too hot in here.
Yeah. Is this normal weather?
This is not normal. This is the hottest. Last time it was this hot was 1976. 1976 is many years before I was born, so this is the hottest I've ever seen it.
Why? What's the reason?
I don't know actually what the reason is. I know it's like, that was the worst snow also in like since 1980 something. I don't remember. It's quite an extreme year this year.
It can be normal.
This is not a normal weather year.
It can be normal in the future.
I hope not. I hope not. Okay, what did we say now? Graphs, was it? Okay, let's start with that now. Atoms. Oh yeah, we do have a bit to do, don't we?
Why didn't you come to our presentation?
I had stupid meetings to go to. Stupid meetings.
With NCP?
No, worse, principal. And other staff members. Boring. So anyways, I told Connell to tell you to say I'm sorry I couldn't make it. I hope you weren't too disappointed. Okay. Just the one graph for this one, was it?
Yeah.
That's okay. Let me just right, so our first column is time in seconds. And the second one is activity in mega BQ. And the time goes in ones all the way up until 10, isn't it? And what's the activity here? 5, 4.21, 3.54, 2.98, 2.5, no, 2.5, 2.10, 1.78, 1.49, 1.25, 1.05, 0.885. Rightio. Step 1, graph this in an appropriate manner. So the appropriate graph here is I should be getting log activity. So that's ln of this. Like that. Yeah. In fact, I don't care about this anymore, so let me get rid of it. Oh no! 1 second. There we go. Alright, can you see that okay? So that's what you should do first. So that's now to make the graph. Okay, so let's do this. Insert chart scatter title. This is activity against time. X-axis is time in seconds. Log activity in. Oh come on, give me a break. Right, you should have this graph. You'll notice it goes a little bit negative at the end. And then we put in the trend line. Huh? Oh, come on, stop being stupid. Right, there we go. So that's the graph. Yeah? Next part. What is the half-life? Oh, sorry, what is the lambda? Do you remember how to get the lambda from the graph?
Yeah.
It's equal to minus the slope. So in this case, the lambda is 0.17. And the unit is, we're using seconds, aren't we? Per second, that's not showing yet. Okay, so that's the lambda, 0.17 per second. And what's the half-life? It's, yeah, 0.69 over 0.17. So, what's that? 4. So the half-life is 4 seconds then. Yeah? And then lastly, no, not lastly, what's the n0? Okay. Oh, come on. Come on, what's taking so long?
Hold on.
The heat, I think. Anyways, the n0, how did I get the n0?
Formula.
Yeah, which one?
A0 equal n0.
Yeah, so then n0 will be a0 over lambda.
Yeah.
So that's 5 times 10 to the 6 over 0.17. What's that? 5 times 10 to the 6 over 0.17?
5 times 10 to the 6. Okay.
What you got?
289017347.
Exactly.
If I didn't think about this,
That's the problem. Tell me why.
but I wrote n.
Oh, mega atoms.
Yeah.
Okay, that's okay. No, that's okay. And lastly, the n when t is 11, so then we just use the formula n equals n0 e minus lambda t.
For D, also that same equation.
Huh?
The same formula. For D, in D.
Oh, n equals n0. Wait, what are you asking me?
For D,
For d.
we use n equals n0 e without inequality.
What do you make equal?
How do we find n0?
Oh, yeah, okay, because you can't use that formula. You have to use the other formula, a equals n lambda.
A equals minus n lambda.
Sorry, minus n lambda, yeah.
Okay.
That will give us the n0 because we know the a0. Yeah. Is this one okay? Are you sure?
The unit for n0.
It's not really a unit, it's just number of atoms, you know.
Oh, do I have to write the full number of atoms?
I just usually write hashtag atoms.
Oh, really? Oh.
Yeah.
It's okay in the
Ah, yeah, that'd be fine.
Maybe I push
Mega hashtag atoms. I really don't like the mega there. I don't know why, I really don't like it. I would rather you write 10 to the 6. Or convert it into moles. You could use something like micromoles or something. Okay. Next now. There's no questions in this one, but there's questions in this one. Do I need the graph anymore? Or any other questions? I don't think so. Aha! Okay. Uh-huh. Come on! Right! Maybe I have to open up a new one. I'm going to close my calculator because maybe it's using too much processing power. It's very hot, you know. Let me close Dropbox as well. What? Right. I'll need your calculator help here. How much energy is required to balance this equation? So, let's have a look. You have H2. Oh, come on. You're not that hot. There we go. H2 plus H2 becomes helium plus a neutron. Oh, flip off. There. Plus a neutron. Now you'll notice that what will happen is the mass here will be bigger than the mass here. Because here this is going to be two of these. And then your helium plus a neutron, 1.00867. So has anybody worked out what the mass deficit or the missing mass is? Yeah, minus the two sides here.
3.5 times 10 to the power -3 AM.
Okay, so 0.0035, that's it? AMU. Okay, so now, to get the energy, it's just going to be that times the U constant for AMU times the C squared. Okay, so what do you get here?
5.22 times 10 to the power -6. But the mass, the mass in AMU is always also means joule.
The mass should be in kilograms in the... what are you asking me exactly?
Isn't a mass a form of energy? Mass transfer.
Oh, you're saying can you write kg as joules?
Yeah.
Oh, that's too advanced. No. You're not at that level yet. Stick to keeping them separate. Thank you. Okay. 2. Consider the nuclear reaction: uranium plus a neutron equals barium, krypton, and 3 neutrons. What is the value of E? So this one is done again the same way. We have to get the mass on the left, and we'll discover that the mass on the left will be will be more than, of course, the mass on the right. And since I don't have my calculator open, has somebody worked out the difference between the two?
Yeah.
0.18326 AM.
0.18 326 AM here. Thank you. Okay, so then the energy will be this times the U times the C squared, and what do we get here?
2.74 times 10 to the power -11.
Okay. B. How many moles are in a gram of uranium? Well, uranium-235, roughly speaking, from chemistry, it means 235 grams corresponds to a mole of uranium. So that would mean 1 gram would correspond to 1 over 235 moles of uranium, which is 0 point whatever. What is it?
4.26 by 10 to 3.
426
Yeah.
moles. Okay, that's grand.
Is it the same if I use
Totally.
AMU and convert AMU to K?
What? Oh, so much work.
No, I mean, just like, are they the same or are they different?
Convert what to what?
Convert the AMU to kg using the AMU.
In this one,
Yeah.
the 235 grams.
No, the value given.
Oh, I understand. You get the mass of 1 uranium, or
Yeah.
by doing what? 235 AMU. Oh, dude, I don't know if I like where this is going.
235.044.
Yeah.
And then convert to kg.
Yeah.
And 1 divided by that answer.
But look at this thing.
Well, where does Avogadro's number enter this?
You know, look at this
Don't
thing.
they ask you for the? Don't they ask you for the number of moles?
Oh yeah.
I don't know. I don't like this. I don't like it at all. Okay, C. How many nuclei are there? Well, you have how many moles, so according to your chemistry, how do you get the number of atoms or nuclei if you know the mole? Yeah, it's Avogadro's number times the number of moles, which is down here. So if I do, what's it, 6.02 times 10 to the 23 times 0.00426, what do I get here?
2.56.
Wait, slow down, what?
2.56 by 10 to the
20.
21. Oh, it's gone.
Gone! Jesus, come on, come back. Right. D. How many reactions can you produce using a gram of uranium? Right, well, if you look at your reaction formula, to have a reaction, you need 1 uranium, or for every uranium nuclei that hits with a neutron. Okay, in other words, each reaction requires 1 nuclei of uranium. It also requires a neutron, but I don't care where the neutron comes from. And anyways, once it starts to react, we're going to get lots of neutrons flying around. We'll have loads of neutrons. So anyways, we need a uranium nuclei for each reaction. We need 1 of these. Now the first neutron, where does that come from? Doesn't matter. It doesn't matter. It's only 1 neutron. We can get it anywhere. But once this starts to break and make more neutrons, these neutrons can hit into the other nuclei of uranium. So anyway, each reaction requires 1 nuclei. So therefore, the answer in D is the same as C, the number of atoms of uranium that you have. That's a lot of reactions. Okay. How much energy can you get from 1 gram of uranium? Well, the energy will be the answer from part A times the answer in part D, which is the same as the answer in part C. So what do we get here? I just want you to take this number and multiply it by this number. What number will you get? Ooh, my exam results from Griffith College have been released. I wonder will I get my A? I had my final exams 2 weeks ago, so what did you get there?
1.167
Negative 30?
13.
But negative? Oh no, something went wrong there for you.
7.1.
But this is minus 11, this is 21. When you multiply them together, you should get something like a 10 to the 10 in the answer. What do you get, Wimpy?
7.01 by 10 to the 10.
10 to the 10 joules. 6 is mega, isn't it?
This is mega.
9 is giga.
9.
So this is 70.1 gigajoules? Whoa, it's a lot of energy. How much uranium have I got? How much uranium did I use to make this?
Lots of.
No, I didn't.
1 gram.
1 gram. Is 1 gram big?
No.
No. And how much energy did I get? I got 70 gigajoules. 70 gigajoules. Giga from 1 gram of uranium.
That's good.
Quite good, actually. That was part E. Part F. A small town requires 10 megawatts of energy, or rather I should have said 10 megawatts of power. Now, how much is 10 megawatts? How many homes would that be? That would be, I don't know, let's see, one home would on average be using kilowatt, an average of a kilowatt maybe, kilowatt, or 2, so it'd be 1,000. 10 kilowatts at most, 1,000. This might be a home, might be a town of maybe like, I don't know, 5,000 homes, 10,000 homes, you know, something on this scale. So it might be something like the size of Dublin 8, maybe something like that. Or something like this, you know. Well, no, actually, that's too much, isn't it? Well, I don't know, actually, how many? No, there wouldn't be 10,000. I know my hometown has 10,000, but you don't know my hometown, so that's no good to you. It's very far away, countryside. Anyway, I would say one home would use about maybe 1 kilowatt on average of power. So you need 1,000 homes to make a megawatt. I'd say it's about 10,000 homes, about 10,000 sort of apartments or buildings or things like this. Come back.
It gave up again.
Huh?
It gave up.
It did. Huh? She's from the Middle East. This is probably winter for her.
Winter?
This is when she's going out making snowmen and, you know. Oh, come on, it's not that bad now. Come on, Anyway, the last part for this one was, if you had your 10 megawatt town and you had 60 gigajoules, how long could you power the town for using a gram? Come on. Right. Anyways, let me just write it down. So you know that power equals work over time, so time equals work over power, which would be 10 mega over 70 giga. No, I've got that wrong, haven't I? The power is, you need the power, sorry, I'm totally off. Power is energy over time, or work over time. Yeah. So that means the time is the work over power, which is 70 giga over, and we require a power of 10 mega. So I think this comes in as 2 hours.
Yeah, 2 hours. No.
Roughly 2 hours, roughly. So 1 gram will power the city for 10 hours. Although, of course, that's assuming 100% efficiency, which it's not. in total the power system is usually 50% efficient. Half the energy is wasted through heat and all this type of stuff. So I don't say this, but if you assume 50% efficiency and recalculate it, you'll end up getting 1 hour, just so you know. So in real life, 1 gram should power 10,000 homes for 1 hour. So it means 24 grams will power the city for 1 day. So, you know, that's not much, 24 grams. Like, think about how much coal, oil or gas you would need to power the city for the small city, small town for 24 hours. It's not going to be 24 grams. 24 grams of coal is like 1 piece of coal. It's not going to do it. So it's quite amazing when you think about it like this, comparing it to burning coal or burning oil, something like this. Okay. What is the mass defect of copper? Now let me try and open up the calculator and hopefully I won't crash the PC. So, when you look at copper 63, what's the atomic number of copper? 32? No. 28.
That's right.
I don't know. You've got the periodic table. What is it for copper? No, but I want to get it exact. I want to know how many protons I should have in copper. We got a periodic table?
63 minus 29.
No, what is it? Just look it in the table.
29.5.
Okay, so our copper 63 should be made up of 29 protons. Now, I have the table here, but I also have it in the formula book and the calculator, so I'll just use the calculator. Oh, no. So it's 29 protons plus copper 63, isn't it? So that's 34 neutrons. This is what the mass should be. It should simply be 29 protons and 34 neutrons, correct? I should get this. Now let me convert that into AMU, so just so you can see it. What constant is the U on the calculator? 17. Should be 63.5 AMU. Should be. Now, is it? Well, no, because it's 62.91367 AMU, not 63.5. So how much am I missing? I'm missing half an AMU. So that half an AMU is called the mass defect.
How would you periodic table would be different?
No, they would say it in the question, because you don't get a periodic table for the physics exam, so any constants you require from the periodic table will just be stated at the bottom of the question. Okay, so part B, what's the binding energy? So how do I get the binding energy?
This by...
Yeah, this by c squared, but I must convert this back into kilograms. So m times c squared. And what number c on the calculator, sorry?
28.
Now, I don't say it, but we usually use electron volts for the energy because it's so small. So divided by 23, 27, 23. And we probably need to make it mega electron volts as well. Yeah. 551 mega electron volts is the binding energy of copper. That's a lot. If you remember, iron and copper, I think, are up the top of binding energies. they're quite high. And finally, what is the binding energy per nucleon? So that's for the total atom, but per nucleon, what should I do to this? Yeah, 63. So it's 8.75 mega electron volts per nucleon of binding energy. Okay. Is that lesson okay?
Nuclear means one proton and one neutron.
Proton or neutron is a nucleon.
Or neutron. Or.
Yeah.
Proton or neutron.
A boy or a girl is called a person. A proton or a neutron is called a nucleon. Got that? Yeah.
Important.
Quite important
Yeah.
to know. Okay. Okay, that's that one there. These are good questions in the exam because they all just use the one formula. The whole lesson was just the one formula, E equals mc squared, and that's it. Okay, next now. What one is next? This one doesn't have questions in it. Photons. Okay. Still happy from the South Korean victory? Mexico is very happy with South Korea.
That's right.
Because South Korea's defeat in Germany meant that Mexico went through to the next stage. Yeah, so I saw a picture of the Mexican people lifting up the South Korean ambassador. And, yeah, very happy. Okay, an electron is released from a metal surface with that speed when this much light is shone on the surface. What is the work function? Okay, so that's just using the usual formula. HF yeah, equals KE. So I'll just put the work function to the right. And what am I looking for? The work function. So the work function is going to be HF minus KE. Right. I'm sorry, I keep bothering you with all my constants. Which one is H?
6.6.
No. What number? What is it? 6. Now, do we know the F here?
We know, we can find.
We could find it because we know the lambda.
Yeah.
So it's C over lambda will give me the F. Sorry, C 28. C over F. No, sorry, C over lambda gives me the F. Okay, and then what did I say? Minus KE, was it? Or plus K? Minus KE, wasn't it? A half M V squared. V is 1,544,71. That's what I got. What unit should I use? Electron volts. 2 electron volts. Yeah. Okay. Number 2. I can do number 2 here. The photosystem of an organic life form is made up of magnesium with one work function 3.68 and light of 300 is shown on it. How much kinetic energy does it have? So again, we can use this formula, except this time we now say kinetic energy equals HF minus work function. Okay, so I'll just go back here on my calculator. Come on, go back. Right. HF minus work function. Right, what is the F here? Do we know it? No, but could we know it? Yeah. So instead of being 600, it's 300. And then minus HF, 6, isn't it? No, what? Minus work function.
Yeah.
And the work function is 3.68 electron volts, but I need to convert that into joules, so I multiply this by E. Right, so the kinetic energy in joules is this, which we can convert into electron volts if we want to. Do you think I want to? Of course I want to. So in electron volts, it's about half an electron volt of kinetic energy. To the previous calculation? Yeah. How did we get the threshold frequency?
Threshold is the work function will burst of lambda.
Is it?
A H.
Yes. The threshold frequency is the work function over, yes, Wookie, over what?
H.
H.
6.6260 minus 0.6.
That's the threshold frequency. 8.898 10 to the 14 hertz.
A little bit different.
And part C was a very sneaky way of asking you what is the threshold wavelength. In other words, what's the wavelength corresponding to this threshold frequency? That is, what is the maximum wavelength, because we're looking at a minimum frequency. So, we just simply do C, whatever it is, over the previous answer to make it a wavelength. And that's it there. Let's make it micro. 337 nanometers
Is it UV?
is also a UV. Well, actually, it's
UV.
yeah, it's UV. You're right, sorry. Yeah. Go smush. Hulk, go smush.
This type of question is common in the US.
Part 2?
Yes.
I've seen number 2 before. Well, the sneaky part once or twice only. That's wonderful. Okay, number 3. A 10 by 10 centimeter squared photocell, solar panel, is made of copper with a work function of 5 electron volts. The light of 650 and 120 watts per meter squared shone onto the photocell. Okay, how much energy does the plate receive per second? So, this is the thing. 120 watts per meter squared. What does that mean? Let's just really think about this. It means if I have a meter squared, then 120 watts will shine on it. But what's a watt? That's a joule per second. So it means in 1 second I get 120 joules. So in 1 second, 120 joules of light will come down. But that's if I have a meter squared. I don't have a meter squared. How much do I have? Well, I have a 10 by 10 centimeters. How many of these squares are in a meter square? 100, isn't it? Because I'll have 10 this way, and I'll have 10 this way. So there's 100 of these little guys in a meter squared. Yeah? So I should divide this by 100, and I figured out on a little square of 10 centimeters by 10 centimeters, in 1 second, I'll get 1.2 joules. So in other words, on a little panel of a 10 by 10 centimeters, I'll get a 1.2 joules a second on the copper from the light. Is that okay? It's not a formula, it's just it's just logic. You just have to think about it. Yeah?
C equal
What?
yeah.
I am. Yes, C system right there. Yes. Okay. Therefore, how many photons strike the metal surface per second? Okay, so you have the energy equals 1.2. What's the formula for the energy of a photon? HF. But that's for one photon, so for many photons it's this. So N is 1.2 over HF. Do you know the F? Well, we could know it. So that's HC over lambda. Or in other words, 1.2 lambda over HC, if you want to write it like that. So let's just take out the old calculator. What did I say the lambda was in the question?
6509.
H is 6 and C is 29? 28. That's how many photons I get per second. 3.93 times 10 to the 18. That's a lot. Okay. Yeah. This. Got that? Next. How many electrons are freed per second from the metal surface? So what's the answer for that one?
1.5 by 10 to the 8.
I think it's 0.
Right.
Because the work function is 5 electron volts.
Yeah.
Okay? So what's the threshold frequency? The threshold frequency is work function over h, which is 5e over h, which equals (1.21 10 to the 15). Now, what is the frequency of the light we're using? It's c over lambda what's the lambda?
6509.
The it's 4.61 10 to the 14. So what's the problem here? No electrons are freed because the frequency of the light we're using, it's 10 times too small to free any electrons. It's lower than the threshold frequency. The photons don't have enough energy to free any electrons. So nothing is freed. No electrons are freed. I was trying to trick you. I was trying to hope a lot of people would say this answer. Did anyone say this answer? Be honest. Nobody? What answer did you say? Alright, okay. It's okay? So part D, what's the current? Well, it's 0. There's no electrons freed. No. Part E now. The copper is replaced by a material known as stibinium with a low work function of 1 electron volt. What is the current now? Okay, so 1 electron volt, that's definitely a very low work function. I can very confidently say, without even calculating it, that each photon will free an electron because the threshold frequency is going to be much, much lower. In fact, it's going to be 5 times smaller. So I won't even bother calculating it. I know the new threshold frequency will mean that this frequency of light will be big enough. Okay? So it basically means that the answer will be, you'll get 3.93 times 10 to the 18 electrons freed in a second. Now, if that many electrons are freed in a second, it means the charge that's released in a second will be this number times E. So I get about half an amp, like about 630 milliamps. Yeah? The current is 0.63 amps. Now I don't ask you this, but I'm going to ask you it now. We could also work out the voltage. How could I get the voltage? What formula would give me the voltage? Any idea? I could use this formula. P equals IV. Because I know the power. The power that comes out of the solar panel, listen, the power that comes out of this in the current, that must equal, by conservation of energy, the power that goes in. And where is the power coming from? Well, it's coming from the light. Well, but also I suppose electrons are freed. No, then it gets a bit complicated. No, actually, I left it out for a reason. Forget I said anything. That is the end of the question. I'm not adding in any extra parts. 0.63 amps. Because also the... Yeah, no, actually, I'm going to stop talking. 0.63 amps.
Isn't that the cube?
Huh?
That's the charge, right?
Oh, the previous answer? Yeah, but because everything is per second, this is charge per second, which you can call an amp. Did anybody actually get that? No. Okay.
Could you please go back to the question?
Yeah.
Oh, and what?
For C, there's no workings really. I just concluded that because the threshold frequency is this, and the frequency of the light that's on it is less than the threshold, it can't free any electrons. Of course it's not. I mean, yes, I did discover it. What happened was I was looking up work functions of metals and I couldn't find one low enough, so I just made up one. Okay, you got that? We can look at the next one. The lowest energy an electron can have when orbiting a proton is minus 13.6 electron volts. This is called E1. The second is minus 3.4 E2. How much energy is lost if an electron falls from state 2 to state 1?
Boom and boom.
Boom minus boom. Okay.
That's it.
Please don't confuse me.
Boom is 3.4.
Minus 3.4 minus 13.6. The answer is, boom, 10.2 electron volts. Correct? Okay. In order to keep the energy conserved, the electron will release a photon, emit a photon. What is the frequency? Okay, so we can say that this energy should equal what?
HF.
HF. So if I divide this by H, I get the F.
Yeah.
Small problem though? What's the problem with this?
You have to change the electron.
Yeah, this is in electron volts, and so first I should change it into joules. Okay, so my photon needs this much energy. So this equals HF. So I divide this by H. Oh, come on, stop doing that.
No, fix it.
Oh no! Hold on, I can fix this. That's it. That's the frequency I need. Okay? B part 1. While in energy state 2, a photon is fired at the electron, and the electron reaches just about energy state 3, which has this energy. What is the frequency the photon needs to make the electron jump from 2 to 3? Well, first we should work out how much energy is needed to jump from 2 to 3. So, state 2 is minus 1.51 electron volts, and state 3, state 3 is 3.4, isn't it? Yeah. So I require 1.89 electron volts of energy. Or in other words, I need this much energy to jump from state 2 to state 3. That comes from the photon, whose energy is HF. So simply by dividing by H. Dividing by H. This is the frequency I need. Okay? Next, while in state 3, a photon is fired and the electron is freed, how much energy do I need to free the electron?
7 miles.
Which is how much? I need, well, what's the energy state? Minus 1.51. So to free it and to bring that to 0, I need 1.51 joules of energy, EVs of energy. So I would need this many joules to free it, which I get from the light, which equals HF, so I divide it by H again. And I need this frequency. Oh, I don't even need the frequency, sorry, I just need, I don't even need that. How much energy do I need? Answer, 1.51 electron volts. That's it. Because the energy it has in state 3 is minus 1.51 electron volts. What energy does it have while it's in state 3? Minus 1.51 electron volts. And to be free means it has no energy. So 0.
So the answer is 1.
Sorry, the answer is just 1.51 EV. Yeah? Now, part 2. An electron's accelerate through a potential difference of 10 kilovolts. It strikes tungsten with a work function of that. What is the wavelength of the photon emitted from tungsten? We were discussing this. I wasn't sure if I was being sneaky, wasn't being sneaky, or what. So let's have a look at this. I think we perhaps decided I wasn't. Let's discover. So, let's see. Let's just draw a good picture of what's happening, okay? So, we have an electron. It enters an electric field and accelerates through the field. and continues out of the electric field and strikes a piece of tungsten. The electron hits the tungsten and becomes stuck, and then releases a photon. Okay. Now, I don't know. I think maybe we need to consider the 10 kilovolts. I just don't know. Maybe I should have written the question better. Oh well, let's see what we can do with it. So the electric field is going this way, and we said it's at 10 kilovolts, and the work function we said is... Oh, I gave it in joules. How weird of me. 7.2 times 10 to the minus 19 joules. Right. We need to be really careful here about the energy. Let's really think about this. The way I see it, there's 3 stages here. No, actually more than 3 stages. There's the electron here before it enters the field. Then there's the electron when it exits the field. And then there's the electron that strikes the tungsten and releases the photon. Now the energy of the system has to be the same in all 3 states. Okay? So at the very beginning, what is the total energy? At stage 1, what is the energy? I'll write it like this. Energy in stage 1, energy at stage 2, energy at stage 3. And then, Audrey, what we can do is we can choose which 2 to say are equal, because they should all be equal. Okay? So perhaps then I might not need the 10 kilovolts. We'll see. Okay, what is the energy in stage 1? What is it? Just before the electron, or rather when the electron enters the electric field, just at the point of entry, what energy will the electron have? Potential. Okay, good. Potential. Potential. But don't forget, what energy does the... is there anything here? No, there's nothing here. It's just potential. Yeah, okay. Now, at stage 2, when it exits, what energy does it have? Kinetic. Okay. And then stage 3, this hits this. So, the energy the electron now has is what? Minus the work function, because it's become trapped in the metal. But it's released a photon, which has energy HF. Yeah? So, I don't know if I should say there's also some heat energy made by the metal when the electron hits it. I don't know then if I have too many variables. So let's just see what we can get if we just leave it like this. Do I know the formula for PE? It's QED, and E is V over D, so it's going to be QV, and it's an electron, so the electron's going to be E V, which is 10,000. So the energy will be 10,000 times E, which is actually 10,000 electron volts, if you want to. But anyways, it's that. Do I know the kinetic energy? No. But at least I know it's actually the same as 1,000 E, because E1 and E2 have to be the same. So really, I have to say then this must also be the same as 1,000 E. So I don't think I should add in heat, because then I can't solve anything. So I guess I wasn't picturing heat here.
10,000 or 1,000?
Oh, sorry, I'm saying 10,000. I'm like, but it is 10. Yeah, sorry. So I'm missing a 0. Thank you. So then HF will equal work function plus 10,000 E. So then the F will be that over, I am looking for the F, haven't I? Yeah, over H. Right. What did I say the work function was? Say again, sorry?
7.2 or 10 to the minus 19.
So do need to know about the 10,000 because I'm putting the 10,000 in this formula. Yeah, so actually the 10,000 is relevant then. 23, yeah, and then 6, isn't it? Now that's a big frequency. I'm curious to what the wavelength is, because I think the wavelength makes it a little clearer of what we have going on here. 28 over my previous answer. So the wavelength is, let's divide it. Can you see it's not even 1 nanometer? What was the wavelength for visible light? It's kind of between 350 and 550 nanometers. And what did we say ultraviolet was? It's like 300 or something nanometers. Yeah. So 0.1 nanometers. That's really small. What type? What could this be? Not ultraviolet, definitely. Think about the spectrum. What is at the far end of the spectrum? Gamma or X-ray. I think this is probably an X-ray. So what are we left with? What part of the spectrum is this in? I'd say it's X-ray. It's a microwave oven. All light, all these things, they're all going to be more than 1 nanometer. Like less than a nanometer is very, very small. You're going to ask me something else, Ray?
What is the electrical stuff going over this?
Huh?
The electric field is going to that.
Because I need this side to be positive and this side to be negative, so the electron will move rightwards. Yeah. By the way, this is exactly how they make an X-ray in the X-ray machine at the hospital. They take an electric field, they fire an electron through it, and it hits some tungsten and releases an X-ray, which they point at you. It's quite a simple machine. I invite you to make one at home, because think about the things you need to make one. Not much. First, tell me what you would need. Go to the junkyard. What things would you need to collect? So what should you get first? Some metal. What would be a good piece of metal to get? Get a piece of copper. Something like this. Yeah? Okay, so get yourself 2 pieces of copper and drill a little hole in it. Yes? Okay. What should we do next? We should put it inside a plastic box, and you can get a little pump connected to another hole here, and the reason for the pump, just like a regular pump, even like a water pump that uses to pump water in a fountain, you're just trying to get some of the air out of it, suck some of the air out. Okay, so you can pump some out. You can get a little electric light bulb, something that just gets really, really hot, and the reason for this is you want some electrons to jump off the surface. Then you need to connect it to 10,000 volts. But how could you make 10,000 volts? I mean, this here is only 220. Well, what device makes a 10,000 volts? No. Transformer. Yeah. And what's a transformer? Well, a transformer is just a piece of iron with the wires wrapped around either side, isn't it? You could again get the piece of iron from the junkyard. Okay. Now the tungsten might be a little bit hard to get, but I think some frying pans use tungsten as a non-stick. So you could get an old frying pan, give it a clean, and stick it here, and put it at 45 degrees. So the electron comes out and hits this. Now, maybe you don't want to stand here. Maybe you could just, I don't know, put a dog or something here. You know, something that nobody would miss, perhaps, stray dog. Now, lastly, you need something for the X-ray to hit to make the picture. So, I think something like some photographic film, you know, like they use in the old cameras. I also think you might be able to use an old record, like an old-fashioned record from like the 60s and 70s. I think this also will react to the X-ray, I think. I'm not sure. So you could use something like this to get the X-ray image. You just want to put it behind the dog so that the X-ray passes through the dog and hits the film, and then the image will form on the film. Okay? No. But you know, if something goes wrong with the experiment, you just, you know, it's for safety reasons. Not if you do this once. You would need to do this at least, I'd say at least 20 times in a very short period. Like maybe in the space of a day or a week or something, you know. I think the recommended limit is 1 X-ray per month. They don't like you doing more than this because then it starts to increase the risk, you know. Every X-ray, there's a risk that it causes damage. So the threshold for medical safety is 1 X-ray per month, I think. So, for example, it's okay to go to the dentist once a year to get your teeth X-rayed, but the dentist is at risk because they might be doing an X-ray 5 times a day, every day of the week. So this is why the dentist is not near the X-ray machine when the X-ray is being taken of your mouth. You notice that if you had an X-ray, they'll step behind a screen. Because for the dentist it's quite bad. Yeah? Or exit the room even, which is safer. In the beginning, the dentist didn't do this. The dentist would used to hold the film up on your tooth and take the X-ray, you know, back maybe 100 years ago. And then after some time, the finger starts to turn black and off it falls. So quite bad for the dentist to have X-rays every day of the year. Not good for the finger on the tooth. Yeah. But for you, it's okay. It's only once a year. You know. Okay. I think is that it for that one? Yeah. Wonderful. If you do make an X-ray machine at home, please tell me how you get on.
One time I saw this thing like if you open Scotch tape fast in the dark, it could make
Maybe it doesn't make an X-ray or just glows.
It glows, but it shows you.
No, I don't believe this. This is outrageous claim. Where did you see this? You believe everything on YouTube? Oh, okay. I'll have to check this out. Scotch tape X-ray powers. I'll see what I can get.
It's your ear.
Hang on. I'm not. It's the wrong screen. This one.